Hi, my name is Ken Brown from a company called LCR Embedded Systems. Today I'm going to present a presentation called Feeling the Heat, Solving Thermal Challenges in a COTS But World. So who is LCR? Every year when we do this presentation, we try to give a perspective of the chassis manufacturer. We feel it's somewhat underrepresented among all the board guys and software guys and system guys, that the guys in the ground making all this stuff work together and keeping it protected and cool get ignored a little bit. So from LCR's perspective, what are we? We're a embedded systems designer specializing in custom systems for the mil-aero market. We do for the Raytheons, the BAEs, the NavAirs. What is COTS But from the title of my presentation? COTS But is basically standards-based designs, but with a custom portion of them. Customers often want a COTS-based solution, but they also want a solution that's going to be tailored to their exact needs. What does that mean? That means they want a documented system, they want a tested system, they want a validated system. They don't want the extended lead times of product development, they don't want the risk of product development, and they definitely don't want the cost of NRE for developing new product. But they do want a system that's going to house the blades they want to see, that's going to get mounted in the structure they already have existing, in the environment they're trying to tailor it to, that hooks up to their power systems and their cooling systems. We've mentioned this last year, and it continues to be true. The VPX market is just growing stronger than ever, particularly in the industry we're in the mil-aero industry. Not just VPX either, but it's VPX in particular, 3U conduction cooled. For LCR and the company and the work we do, that alone is accomplishing about 75% of our new designs. So you have the challenges of VPX, you have what the market and the mil-aero industry is asking for. When those two things collide, you end up with a whole new set of challenges that you didn't have in the past. Previous to the position I'm in now, I was a mechanical engineer for 10 years designing these chassis. Back when I was doing it, it was just VME. Just VPX kind of took off right after I got into this new role, and these systems have just ridiculously grown in complexity. They're so much more intelligent, they're using so much more power, they're going in smaller packages, they're going in more extreme environments, and it's just upping the challenge every day for the engineer working on these boxes. Last year we did dive into this a little bit, mostly to talk about the challenges of all the I/O that VPX can handle. This year we're going to dive into the thermal challenges that presents. So the mil-aero requirements they always want more processing. What does that mean? That always means more heat, right? They continue to make these packages smaller. What does that mean? Higher thermal density to go along with that more heat. And they continue to enter harsher environments. And as these systems become part of unmanned systems, suddenly the vulnerabilities of man no longer come into play because these systems are going in places that man was never meant to be. So we have our poor mechanical engineer here, chassis designer. He's got a customer with ever-increasing requirements every day, every year. Doesn't want to pay more for those requirements. Doesn't want the prolonged schedules of designing for those no requirements. And yet, this engineer has to meet those requirements. Throughout the years, LCR has some lessons learned from trying to meet this COTS But requirement. Early on in my days, I came to the conclusion that lessons learned is really just a nice way of saying times we screwed up that we don't want to screw up again. First thing would be requirements inflation. I think every engineer in here has probably been a victim of this at some point. You have the system designer. He knows he needs this much processing. Just to be safe, he's going to double that processing requirement to make sure he's covered for whatever the software engineers put into place. Then you have the guy that's kind of picking the blades for the system. He picks a processor that's double what the previous guy put in place. Then you have the mechanical engineer who's writing in the thermal dissipation levels required of the chassis. He adds 50% more in there as well. Suddenly you have a requirement where you only need 25 watts of processing, but the spec you're being given is asking you for 100 watts of cooling in that slot. Something to be very careful of as you're moving into that. We actually had something happen recently where we were doing a custom power supply for a company, and they had to be 250 watts, had to meet these requirements, had to fit in this package. We got it done. It wasn't easy. There was a lot of lessons learned along the way. At the end of the day, they were using so little power that the voltage regulation on the power supply wasn't even pulling enough juice to regulate the voltage. Simulations and analysis. These can go a long way. What do they go a long way towards? Really, they go a long way to making sure that you have the most efficient and effective airflow and/or cooling design in your chassis. What they don't do is give you guarantees. Even though it gets you that best airflow that you're going to get, it's not necessarily that great, at least that I found, at predicting the exact temperatures you're going to see. So what does that mean? Basically, instead of a design that might take 5 iterations to really get it right, simulation might cut you down to 2 or 3 iterations. This is in spite of every project manager and program manager that would love to believe that your simulation that shows good results is a guarantee when it comes down to making this new product. You still need to test and validate that system. Make sure you don't rely on that simulation. Prototyping, even further risk development. Who here has the schedules and/or the budgets for prototypes? As much as we'd all love it, it really can't be done. What we are seeing, though, that even though you might not be able to prototype of your full system, the advent of rapid manufacturing and 3D printing, it does give you an opportunity to mock up some portions of that system and really give them a test run. Again, you might not get the exact results you're expecting, but it'll give you a feel, are you on the right path for where you're going? So what are the options as far as your thermal solutions come to play? Basically, it comes down to 2 very important factors, performance and cost, pretty much what every engineering decision comes down to. How much performance do you need, and how much are you willing to pay for it? While cost and performance are very important, they're not the only factors that matter. Payload, are you cooling a large air-cooled ATCA card, or are you cooling a 3U conduction-cooled card, right? Definitely matters. Weight, is this going in a fixed ground stationary environment, or is this flying in a UAV that's the size of a person? Environment, are you in a controlled environment, or are you on the deck of a ship? Right? Definitely factors to consider. Infrastructure, is this thing sealed away with no support whatsoever from a cooling perspective? Or is there fresh air available? Is there a liquid cooling supply available? Life, you can have systems that are just straight conduction cooled that can last nearly forever, while a system with a fan is going to have a very short life compared to that. This is the options we're going to go through. I tried to rank them from performance. That being said, there's a lot of overlap in these. First one we'll cover is natural convection. It's very simple. You don't have to add any parts to it. You don't have any moving parts. It generally doesn't need any support from the infrastructure around it. You can use a sealed solution to protect from the environment around you, but it's going to give you the worst performance of all your choices. For all but the lowest power consumption, this just isn't going to cut it. Conduction would be the next one in play. Still inexpensive, still doesn't require any additional parts. Doesn't require any moving parts, still a sealed box, still very rugged. Does require a little bit more infrastructure support since you're going to need to sink that heat from the cards through the box to something, right? It is minorly, or just a little bit better performance than straight natural convection, but still not going to cut it in a lot of cases. Forced air, probably the most common that we've seen up until some of these UAV systems came around. Very inexpensive, very common, very quick to design. It's low risk, and you can still get decent performance. This one's probably runs the most performance gamut, depending on if you have the space for the fans, the power for the fans, and if you're willing to go through some hearing loss, you can get as much cooling as you want out of a forced air enclosure. It generally does need a controlled environment, though, because if air's coming in, other things are coming in, right? You can use filtering, that's really going to cut down on your thermal solution, but you need to be in a generally clean environment and a moisture-free environment for forced air to really be effective. Liquid cooling. Now we're starting to get up there, right? The performance is really starting to take off, so are the requirements. So you can get a really high performance out of this liquid cooling. You're going to have longer development cycles. The manufacturing required for some of the liquid cooling components is longer. You got a little bit more risk. Now you have fluid being introduced, electronics, not a great mix. You need a decent support infrastructure now. You got to have a circulation system and the pumping system and the heat exchanging system all has to be in play. Sometimes you got room for that, but when you're on a UAV, I don't think anybody's got the room or can handle the weight of having a liquid circulating system in there. It can also get very expensive. Now we kind of top into even more exotic methods, right? I myself have never actually designed a system that uses spray cooling. I've seen them on display and demoed for me, but it gets you really high performance. That liquid is getting right to the heat source, right? But the infrastructure, the risks, the development, you just take what was the closed loop liquid system, and now you're just magnifying all those even more, right? You need the supply system, the spray system, the collection system, in addition to all the heat exchanger systems and all that. So those standard techniques that I just went through, those generally will work okay in the standard environment. When it comes to COTS butt, it's going to need a little bit more. You're going to have to get into hybrid methods. Hybrid methods comes with a little bit of a note. Really, every method is a hybrid method, right? Even if you're having a natural convection cooled chassis, you still got to conduct the heat to the outside walls before natural convection can do its thing, right? Even if you got forced air, you still got to conduct the heat to a finned heat sink to let the forced air do its job. We're going to focus on more where there's more of an even balance between the two methods in the system. Then we're going to get into bending the rules. The one benefit we have of a COTS butt system is that we can bend the rules a little bit, right? This system isn't designed to be used universally. It's not designed to be used anywhere else. It's being designed to this one customer's specific application. First hybrid method, I'm sure everybody's seen this. Forced air over conduction. You get to use those really rugged, sealed VITA 48.2 cards. They conduct to that outside wall where you get the forced air blowing over it. So you get the benefit of those rugged cards in the sealed chamber, and you get the increased performance of the forced air. Forced air. Here's where you have basically, you have a sealed inner chamber again. So you're protecting those sometimes more vulnerable air-cooled cards. But you're circulating that air in there. You're conducting it through heat sinks to the outside wall, blowing cooler air over it again. So you get that benefit of the high performance of forced air and still get some of the ruggedness of having that sealed inner chamber to protect those cards. Now we'll get into bending the rules a little bit. VITA spec has a few pitches, right, that you're allowed to use for VPX. But when you're in the COTS butt world, you can push the envelope on that a little bit. You push that board pitch out, plus it's past the 1 inch mark. You reduce that thermal density. That can go a long way towards helping your cooling. You don't necessarily have to double it or triple it. Just as small increments as 1.2, 1.4 inches can offer you a big help by reducing that thermal density. Once you've done that, you can take it one step further. You got the room, you might as well force some air into there, right? Even on cards that aren't necessarily designed to have that air blowing across them, some air blowing across the conduction cooled card is really going to help. Just forced air is just that much more powerful as far as performance is concerned. Now, if you want to go even further, you can add a dash of innovation. We talked about the hybrid performance, how they all use conduction to some extent. Anywhere where you have conduction as part of your thermal solution, something like a heat pipe can really go a long way, right? It takes what would normally be a very concentrated source of heat and really spreads out that thermal density. It makes it a lot easier for the thermal engineer to cool it off. One more piece of innovation you can have is composites. The most popular probably being carbon fiber, but there's many different kinds. Many people, under first glance, assume that carbon fiber is a terrible thermal conductor, and under most cases it is. But when designed correctly, it can actually offer significant improvements over aluminum as far as conducting heat is concerned. It does get into more specialized composites, and it can get very expensive, but when you need that high performance, sometimes you are willing to pay for it. So there we have our thermal engineer. He used some of our lessons learned. He considered all the options. He's combining different methods. He's bending the rules a little bit, throwing in a dash of innovation, and now he solved the problem. It might help as well that they gave me a computer, it looks like, from the first time around. Certainly that helped. If anybody, there's the 3 of us here from LCR today. If anybody has any questions later on or wants to discuss any of this, we'll be happy to discuss it with you.